Oké, goedemiddag, welkom allemaal. Fijn dat jullie hier zijn voor alweer het 5e seminarium, denk ik, dat we hebben. En deze keer uit eigen huis, niemand minder dan Sietske Tacoma, die in juni, als het goed is, haar proefschrift gaat verdedigen. En het onderwerp daarvan is hetzelfde als het onderwerp van haar voordracht vandaag. Moet ik nog meer over jou zeggen, Sietske?
Nee, de rest vertel ik zelf.
Oké, perfect.
For the video I will present in English, but feel free to ask questions in Dutch. So I worked on my PhD research for 5 years, and summarizing or presenting 5 years of research in 1 hour is a little bit ambitious, so I will try my best. But if I don't make it to the end, so please keep track of the time, and otherwise I will come back another time. I will end with a nice cliffhanger, so you will have to invite me once again. So, who knows what the mortality rate of the coronavirus is? Between 2 and 4%. Nobody knows. Estimates. This is an example of how important and how omnipresent statistics are in our society. And the United Nations also recognized that statistics is very important in our society. So they issued fundamental principles of official statistics. And the first fundamental principle of official statistics states that official statistics provide an indispensable element in the information systems of a democratic society. And therefore, official statistics should be made available to the general public to honor citizens' entitlement to public information, well, etc., etc. The point here is that statistics is very important. And as you all know, statistics is very important in science too. So university bachelor programs all include, or almost all include statistics courses in their bachelor programs. And here is a typical task that you could come across in a statistics course. I'll give you a minute to read it. So reading this task might make you think back of when you were a student yourself. Maybe you can still imagine yourself sitting at your desk thinking, yes, long story. I think I need to do something with a hypothesis test, because that's what the teacher's been talking about, and it says do a test. So yeah, what should I do? I think I'm gonna need hypotheses, I guess. Something with a critical value. There was something with a critical value. I need to do some steps. Okay, so you're struggling a bit behind your desk, making some steps, finally coming to a conclusion. Say you reject your null hypothesis in the end. And then often in such courses, when you had been working on such a task, you would have an answer booklet available. So you take the answer booklet, look up the answer, compare it with what you've written down, and it's completely different. Recognizable? I mean, it happened to me. I'm pretty sure it happened to you as well. And it's frustrating, especially when you've been working for a long time on that task. So, one thing we did in my PhD research was look whether computers could help with such frustrating issues. The first question in my PhD research was how can computers be used to give useful automated feedback in multi-step hypothesis testing tasks? And we had several aims with this feedback. So one was to provide guidance along the way. So after each step a student adds to the hypothesis testing procedure, the computer could give feedback on whether or not the student was still on the right track. But we also wanted to give feedback on the meaning of the hypothesis testing procedure. What is it that you're doing when you're doing a hypothesis test? Because hypothesis testing is a technique that is very often used in statistics. So one way to offer such feedback could be this. Here every step is spelled out. So we state hypotheses, we state what the significance level is, tell something about the population, something about the sample, then we calculate some things, etc., etc. The computer provides all the steps, and when you fill in the steps, the computer provides feedback on whether or not you completed the steps correctly. Well, this can be helpful, but a downside of this approach is that it takes away the reasoning. So the student doesn't have to do the reasoning. That's already on the screen. So what we wanted was a more open approach. And what we designed was a system, actually a list of all the possible steps that a student could want to do in a hypothesis testing procedure. And the student could freely choose steps from that list. And every time the student chose a step, the contents of that step would appear on the screen and the student could complete the step. And then again, after completing each step, the student could press this check button, which is there at every step, to see whether the solution so far is still a correct partial solution. And the challenge here was to design feedback that could manage all different orders, that could manage this free task, this open-ended task structure. And we did so using a domain reasoner. So let me first give you an example of feedback that we gave. Here you see that this is already step 2. So the student already did a correct step before, which was stating appropriate hypotheses for this task. And then the student thought, okay, I have to find a critical value. I'm doing a z-test, so I need a critical z value. And I think it's 1.33. Now that's not the correct critical z value for this task. Actually, it's 2.33. But 1.33 does happen to be the value of the test statistic in this task. And our software knows that. So our software is programmed in such a way that it recognizes, hey, this value here, this 1.33, that is the value of the test statistic. So maybe this student at this point has been confusing test statistic and critical value. So it provides feedback. What exactly is the critical value and what is the test statistic? So this was what we offered students in an experimental condition. And I will talk a bit more about the experiment a little bit later. I will first say something more about the design of the feedback. But to compare, this is what students in a control condition would receive. In the same situation, students would, also in a control condition, the students had the open-ended task structure. So they could also select the steps from the menu. But they only received verification feedback. So they only, for each answer box, they received the feedback whether that answer box was correct or incorrect. So here, in this case, the feedback tells less because it doesn't tell what is wrong with the test value, only that it is wrong. Yes?
Do you do all feedback in form of questions, or is that coincidence now?
No, it's not always questions, but what we did try in formulating the feedback is not giving away the correct answer and trying to stimulate the student or encourage the student to think about the concepts involved rather than just telling what's wrong. So how did we arrive at such feedback? This is called, the system that we designed is called a domain reasoner. My promoter, let me do a short intermezzo. My promoter for this PhD project is Paul, and the second promoter is Johan Juring from the computer science department. And I also worked a lot with Bastiaan Heeren, also from the computer science department. They have a lot of experience with designing domain reasoners, and mainly together with Bastiaan, we designed the domain reasoner for hypothesis testing. And our domain reasoner consists of a set of constraints and a set of rules. And a set of buggy rules. So constraints basically say, if a partial solution satisfies this condition, then it should also satisfy that condition. So if a partial solution contains a value for the critical value, and the alternative hypothesis is this and this and this, or looks like this, then this critical value should be this. Constraints can also be if the solution contains a conclusion about the hypotheses, then it should also contain hypotheses. So these constraints basically check the coherence of the solution and checks whether the different steps match with each other. Then the rules only are used when no constraints are violated, because when no constraints are violated, the partial solution basically is correct. So there's no error, no inconsistency in it. And then we use the rules to discover what the student did precisely. So for example, a rule can be calculate the value of the test statistic and then add it to the partial solution. So the rules basically are adding new steps to the solution. And then buggy rules are also adding new steps to the solution, but doing so in an incorrect way. So here, if you follow the scheme, it's an incorrect solution. So at least one constraint is violated, namely the constraint saying that if the solution contains a critical value, then this critical value should be, after some reasoning, 2.33. So we go this way. And then we try to discover whether a buggy rule was applied. And in this case, a buggy rule was applied, namely the buggy rule that says add a critical value, but with the value of the test statistic. So use the value of the test statistic instead of the critical value. So we report a feedback message corresponding to this buggy rule. Let me give you one other example, this one. What happens here is that the student, as a first step, tries to determine a rejection region for a task in which he or she is going to do a z-test. Now, in essence, this step is correct. So in the control condition, you can see it's just marked correct. But what we wanted to do with the domain reasoner was encourage students to think about the logic of hypothesis testing. And when you think of what the steps in a hypothesis test mean, a rejection region doesn't mean much if you don't know what you're testing. And if you don't know whether your alternative hypothesis is one-sided, left-sided, right-sided, two-sided. So that's what we address in the feedback. We try to encourage students to first state hypotheses. Now again, we can show how that works in the scheme. Is a constraint violated for this solution? Yes, the constraint. If the solution contains a rejection region, then it should also contain hypotheses. Was a buggy rule applied? No. So we report an error message for this violated constraint.
So why is this not a buggy? Is this not a common mistake? So it's not an identified common mistake?
No, and it is already, maybe more importantly, it's already captured by the constraint. So we didn't need to put a buggy rule for this specific situation because we could already catch it by only looking at the constraints. Whereas the previous one, we couldn't catch it with the constraints because the constraint only said that the test or the critical value should be 2.33. Well, it wasn't 2.33, so that constraint was violated. But that didn't give the information that the value that the student had given was actually the value of the test statistic. So it didn't give us the information about the confusion between these two concepts. All right, so that's about the design of our domain reasoner. Now yes?
I forgot what you said in the beginning, but you can ask questions.
Yes, you can, yes.
So I was just wondering how this domain reasoner looks like. Is this some general graph for a domain, or is it something you describe for each task?
No, it's a general scheme for the whole domain.
Sietske, can I just ask you one thing? Can you
Oh, yeah.
repeat the question?
So,
Because otherwise it's not.
Michiel's question was whether the schedule is specific for each task or whether it's general for the whole domain. And it is general for the whole domain. So what we feed the schedule is a starting situation for the task. And that consists of an alternative hypothesis, the significance level that we use, and some sample statistics. So the sample size and a mean, standard deviation, things like that. And if you provide that information, then the domain reasoner can calculate all the other steps from there. And that's what we use the rules for as well. That's what the rules are very important for.
Okay.
Does that answer your question?
Yeah, but maybe I will ask another question related to this at the end. Because
Okay, keep it in mind. So what we did was an experiment with, well, I just showed you the experimental condition and control condition in a university statistics course for social sciences students. The scores looked like this. They had 5 homework sets in 5 separate weeks of the course. There were 2 intermediate exams in between. So these dots are weeks. And then there was a final exam at the end. And the 3rd, 4th, and 5th set were all about hypothesis testing. The first one was about descriptive statistics, and the second one about the normal distribution, I guess. And what we did in these 3rd, 4th, and 5th homework set was add 2 of these open-ended tasks in which students received feedback from the domain reasoner. Most homework sets contained about 10 tasks. So in 2 of these 10 tasks, students constructed hypothesis tests step by step. Well, and then we looked at their work on these 6 tasks, and that we found this. So on the left-hand side, you see the percentage of students who solved each task in both groups. And you can see that in the beginning, students in the control group, more students in the control group solved the tasks than in the experimental group, percentage-wise. So in the beginning, for the students in the experimental group, it was more difficult to solve the tasks. And we think that that has to do with the stricter criteria. So for a solution to be correct, students in the experimental group needed to provide a coherent hypothesis test because of all these constraints. While students in the control group actually only needed to draw a correct conclusion about the null hypothesis without even having to state the hypotheses themselves. Now, what's nice in this graph is that after working for a while with the tasks, we see that students in the experimental group start to outperform the students in the control group. And we did a logistic multi-level regression analysis to see that this trend indeed was a significant difference between the 2 groups. I won't go into the details of the regression analysis here, but they're all in the thesis. Yes, Michiel?
So how did you select the task numbers?
Michiel asks how we selected the task numbers. These were the final 2 tasks in each module in which the students had to carry out a complete hypothesis test. So for each task, the module homework set 3 was about set tests, 4 was about paired t-tests, and 5 was about independent t-tests. And in each homework set, the students first had some practice and very stepwise hypothesis tests, and then the final 2, we replaced them by the open-ended tasks. And then usually there were some later tasks asking questions about power, type 1, type 2 error, statistical topics related to hypothesis testing, but not the procedure itself. We also looked at the number of errors students made, and specifically the number of errors that students made in the logical reasoning of the hypothesis testing procedure. And there for both groups we see that the number of errors decreases over tasks, so that's nice to see. After some practice they make fewer of these errors, and we see that the decrease is stronger in the experimental group. And especially this tells us that the feedback, the elaborate feedback that the domain reasoner gave helped the students to not make the same mistake again. So after they had made a mistake, for example, drawing an incorrect conclusion based on the data they had, after making that mistake once, they read the feedback and didn't make the same mistake again. In many cases. In some cases they did make the same mistake again, but in many cases they didn't. Now we were also interested in whether, so this is the students' work on these 6 tasks. We were also interested to see whether on later tasks we still found the differences between the experimental and control group. So we selected some tasks in the module that were about parts of the hypothesis testing procedure, but that the students worked on after having worked with these 6 tasks. Well, and then we didn't find any differences between groups because it's this here. So they were really exactly equal. But we also looked at tasks on other topics that were in the modules in between those follow-up tasks. And then we saw that they performed pretty well, significantly better on the hypothesis testing tasks. So what we thought here is that in general, working with the open-ended tasks in which the students had to select their steps may have contributed to their understanding of hypothesis testing. But, well, this is, as an experimental design, it's not so strong. So these are pretty tentative results. Why I wanted to show them anyway is because with the domain reasoner, it is easier to design new tasks on hypothesis testing. So, well, when I designed the tasks, we had a pretty non-user-friendly way of designing hypothesis testing tasks. But in the meantime, I've been working on a more user-friendly way. So this is in the digital mathematics environment, or in NumWorks, where we can define all the steps that a student could want to choose from. And then for each step, define the contents of that step. And when we're not using the domain reasoner, then for each step, for each answer box in each step, we have to define what the correct answer for that answer box is. But when we are using the domain reasoner, as I explained before, we only have to state the starting situation. So we have to fill this, and this answer box to define the alternative hypothesis that the student will be working with. But then the domain reasoner can calculate the null hypothesis itself, can determine from that whether the test is left-sided, right-sided, or two-sided, etc., etc. So designing new tasks is much easier when using the domain reasoner than when not doing so. All right. So coming back to my first question, how can computers be used to give useful automated feedback in multi-step hypothesis testing tasks? I think that the domain reasoner is a useful solution. For a conference in Chicago last year, I made a demo video. So if you're at home in the next 2 weeks because you can't go anywhere else, you can look this demo video of how the hypothesis testing tasks can be solved. Now these statistics courses, they don't only cover hypothesis testing. And luckily they don't, because statistics is more than just doing hypothesis tests. Students need to know, well, which tests there are. They need to know what visualizations they can make from data, or if they see a visualization of data, how it can be used. Is my histogram correct, Lonneke? Useful?
As far as I can see right now, yes, I think so.
So students need, I called it statistical proficiency. An understanding of statistics, knowing how to use it, knowing when to use it, knowing what it can do for you and what it cannot do for you. And therefore, statistics courses cover many statistical concepts, many topics. So my second question was to find out how can computers be used to provide intelligent feedback about statistical proficiency. So this more broad view on statistics. And to introduce that second type of feedback we designed, I would like to ask you to think back again of when you were a student, when you were preparing for your exams, for your statistics exam, of course. Sitting at home at your desk, what would you do? You would probably read the textbook, but how did you know which parts to read? Or you would maybe work on practice tasks, but then how did you know which tasks you would do? How did you know when you had practiced or studied enough? Now these are questions we thought the computer could help with as well. Because when students work in a computer-based learning environment, then they do attempts at all tasks, and the computer continually collects evidence of what a student knows and does not know. Because here, if this answer is correct, then that's evidence that the student knows about, variables. And if this answer is incorrect, then that is evidence that the student has a lack of understanding, some lack of understanding, with respect to percentiles, etc., etc. So what we did was we connected all the tasks to the statistical topics, concepts that they were about. And a list of such concepts is called a domain model. Here's the domain model for this homework tasks I just showed. And based on all the attempts that students did, their correct and incorrect attempts, we calculated a student model. So this is called an inspectable student model because it's inspectable for the student. The student can view it and can use it to think what he or she should pay more attention to and what he or she knows well enough to do the final exam. Boole and Kay have done much research on this. For example, on how to represent such inspectable student models. And one choice we made was to, when students opened the student model, to only show the categories and the scores, so that students could decide for themselves whether they want to inspect the categories in more detail or not. But another choice we had to make was how exactly to connect tasks to concepts, because this is one choice we could make, we made. But for the top two tasks, we could also decide that the first one is, so they're both about variables, but the first one is about dependent and independent variables, while the second one is about continuous and discrete variables. So is that one statistical concept, or are those two different statistical concepts? There are many such choices we had to make when designing the inspectable student models. So after we had designed these student models and gave them to the students, I think after we gave them to the students, we wondered, do these student models that we have designed actually make sense?
Did you have some sort of principles that you used?
Yeah, so we used the literature, so Rogier asks whether we had some principles we used. So we did use the literature by Boole and Kay, for example. Sergei Sosnovsky also had information about student models and inspectable student models. So we did look at literature, but still this decision of finer-grained or coarser-grained student models is a design issue that everybody has to deal with. And coarser-grained models are easier to design. Finer-grained models may result in better, more accurate student modeling, but then you also need enough tasks to collect evidence about what the students know. So yes, we wanted to know whether these student models made sense, and we tried to figure that out using student data. This is what our student data looked like, attempts at the different tasks by different students, and these attempts were incorrect or correct. And what we usually would see was that a student would do some incorrect attempts and then a correct attempt and then move on to the next task. So this is immediately correct, move on to the next task, incorrect, correct, move on to the next task, etc. So usually students would try each task until it was correct. Now what we did with the student data was reorganize it by knowledge component. A knowledge component is a topic, one element of this list of topics in the student model. So these are the same attempts, but now ordered by knowledge component and then by student. And what we can then do is calculate error rates. And error rates are calculated per knowledge component, and then the ratio of student that makes an error in their first attempt on that knowledge component, and then the ratio of students that made an error in their second attempt on that knowledge component. So that's this formula. The error rate for the nth attempt is the number of students who made an incorrect nth attempt on that knowledge component divided by the total number of students who made an nth attempt on that knowledge component. And the idea behind calculating error rates is that for each knowledge component they should be decreasing over time. So when the student first encounters a knowledge component, they often make many mistakes, and then over time, once they've seen a knowledge component more often, they make fewer errors. And the assumption behind this analysis that we're doing, learning curve analysis, is that learning follows a power law, so that this decrease follows this power function.
Sorry,
yes,
I'm just confused. I thought you just said it would increase, that with the attempt, with the first attempt, you have a low number, many incorrect ones?
Many incorrect.
Oh, sorry, it's incorrect and not correct.
All right, so so what we would expect for all knowledge components was to see something like this. Many incorrect attempts in the beginning, and then over time, a nicely decreasing error rate. So we had 5 homework sets, work from 160 students, and in these 5 homework sets in total we had 71 knowledge components. And you can see it on my slide already. For 34 knowledge components we found a nice decreasing learning curve. For 50 knowledge components we did not have enough information to generate a learning curve. So these were concepts that were in our student models, but apparently the students did not make enough attempts on these knowledge components to generate a learning curve from. So we thought that was, well, interesting, because apparently we didn't provide the students with enough tasks on these knowledge components. So first, that was time to reflect, do we indeed want to include these knowledge components? If so, we should add more tasks addressing these knowledge components. And then, we did the calculation already. There are 22 knowledge components left that showed learning curves like this one. And we wrote a paper about this together with Peter, Johan, and Paul, and Sergej Sosnovsky. And Sergej Sosnovsky told me all about learning curve analysis. And when I first came to him with my increasing learning curves, he said, I've never seen increasing learning curves before. So we had to find out what was happening here. And I would like to try to find out together with you. So here's one example of an increasing learning curve. Can you think of a reason why this one is increasing?
What are the dots?
The dots are the error rates for each attempt. So on average, 30% of the students made an error. No, for all students together on this knowledge component of the mean. So 30% of the students made an error in their first attempt on a task on the mean. And then, on the second attempt, 10. On the third attempt, 20, etc.
Too many attempts, maybe?
After 2 attempts, almost all students are gone?
Sorry?
Only few students are left.
Only few students are left. Well, that could be an example, but we used a cutoff criterion. So indeed, you can't go on with these error rates infinitely, because all students will make a first attempt, but some students will only make 6 attempts and others will make 20. So we used a cutoff criterion that we needed to have 2/3 of the number of students with the first attempt left. Otherwise, we thought indeed the learning curves would become meaningless. So we know that here there are still at least 2/3 of the number of students as there are here.
I think they started guessing. So
Rogier
there was
thinks-
a list that was something multiple choice, and they started in the first ones. You have people do serious attempt and correct, and then after that they, I don't know, I'm just going to try them all consecutively or something.
Yes, so you think students started guessing. Well, what is important to keep in mind is that this is one knowledge component, but it's students' attempts at multiple tasks. So what we did in this paper and in the study was look at what tasks do we have. So we used our didactical knowledge. So let us see, what tasks did we have about the mean? These are 3 examples. There were quite some tasks about the mean. Have a look at these 3 examples.
And they are on the same knowledge component?
These are all tasks on the mean, connected to this knowledge component of the mean.
Underlying skill.
Definitely. In this case, these are 3 quite different things we're asking here of students. We're asking them to calculate the mean. We're asking them to judge whether the mean is appropriate for a given situation. And we're asking them to calculate the standard deviation, for which you need to calculate a mean first, but it's not the only thing that you're having to do there. So especially in this case, if a student calculates the correct standard deviation, then that is evidence that the student knows how to calculate the mean. But the other way around, if the student calculates an incorrect standard deviation, then that is not evidence that the student does not know how to calculate the mean. It could be the case, but it might be more probable that the student doesn't know how to calculate the standard deviation from the mean. So in this case, we split the learning curve and we split the knowledge component into the 3 different perspectives or concepts that were initially all combined together in this knowledge component of the mean. A second example, with something different going on.
I would say remove the first attempt and you get a totally different picture.
I would say so too. And why? I mean, we would like to have a didactical explanation for that as well. And we did. We looked at the tasks in the homework set again. And we saw this was the component on the significance level. And in one of the first tasks, the students were just asked to state what is the significance level in this situation. Whereas in later tasks connected to the same knowledge component, they were actually asked to use the significance level in a hypothesis test. So it's a little bit the same as the previous one in that they had to do different things with it. But here it was only one task and that we felt the teachers had included to give the students confidence. So we thought that these tasks were valuable in the homework sets, but they were not very useful for us to base a student model on. So we decided to keep these tasks in the homework sets, of course, I would say, but we removed the connection between the task and the concept in the student model to not use this information for the student model because it was not useful for that. Last example. Most difficult one. If you've read the paper, you know the answer.
Isn't it just spread all over the place? So
Yes, so the fit is rather weak. So yes, it's increasing, but you could say it doesn't say so much. It's easy. Students actually barely make mistakes on this knowledge component. So this thing, we thought, okay, knowing when to reject a null hypothesis, knowing what it means to reject a null hypothesis, we thought that is something very important in the hypothesis testing procedure. But students barely made mistakes on that. So again, we looked at the tasks, what happened there. Well, most of the tasks concerning this knowledge component were tasks like this. Yes, no. So students just had to choose, reject null hypothesis, do not reject null hypothesis. And they could barely make mistakes. So whether they understood it or they didn't understand, didn't really matter. They could just choose yes or no, maybe make one mistake, maybe don't, and then have the correct answer. So the error rates were really low. And this was a reason for us to redesign these tasks, to think of tasks concerning this knowledge component in which the students were asked to reason about the null hypothesis, were asked to, or did get opportunities to make mistakes. Yes?
How do you get more than one attempt at a yes or no question? Or is the other one also, because you say you choose yes or no, but in the graph before this you showed that there are people who had 4 attempts.
Yes, because there are more than one task connected to the knowledge
yes,
components.
Yes. Okay.
Yeah. So this was the reason for us to redesign the task. So, coming back to my question, do the student models that we have designed make sense? Well, we did find some issues, but we were able to identify these issues, to explain these issues, and that gave us enough information to redesign the student models and the tasks. And then we were quite happy with the student models we had designed. So coming back to question 2, yes, look here.
I wonder, is that so the improvement that you made, are these improvements just so that you can have this decreasing curve, or do you also see them as didactical improvements?
I do see them as didactical improvements, so I see the learning curve analysis as a tool to pinpoint weaknesses in the didactical design of both the student models and the tasks. And I do believe that increasing learning curves or absent learning curves, because we use those as well, are an indication that something is wrong. Didactically, yes. So how can computers be used to provide intelligent feedback about statistical proficiency? Well, obviously, by providing inspectable student models. Everybody convinced? I'm happy, I'm handing in my thesis. Done? Not really. Because we didn't look yet at whether the students used the student models and whether they benefited from the student models. So if I look at the formative assessment cycle, which I just picked from the internet, students have worked on the tasks, or they have been given tasks, they have thought about the tasks, they have given answers to the tasks. Then the computer has collected evidence and has provided feedback, but we didn't look at this step yet for the student models. Did they use the student models, and if so, did they benefit from it? So, that's my question 4, and I will take the domain reasoner with it as well. So do students benefit from the availability of the domain reasoner and of inspectable student models? And let's look at the time. Yes, I can still talk for 10 minutes, right? So one thing we were happy to see, this is the students' use of student models throughout the course period. And what we see is the light gray areas are sessions in which the students worked with the computer-based learning environment and did not look at the student model. And the dark gray areas are sessions in which the students worked in a computer-based learning environment and did view a student model. Now, first thing that you can see is that they looked at their student models in about 30% of the sessions they worked with. What you can nicely see in the graph is when the homework sets were due, and especially when the intermediate exams and the final exam were. And what we were happy to see in this graph is that students kept looking at their student models throughout the whole course period. So that is an indication to us that students found these student models useful, because otherwise you would expect that they looked in the beginning and then they would never look again. So that's nice. Then we did an experiment with both feedback types. And I realize now that I say inner and outer loop feedback here. Inner loop feedback means feedback on steps. So that's the domain reasoner feedback on the hypothesis testing tasks. Outer loop feedback means feedback over larger collections of tasks. So that's the inspectable student models. Now we set up an experiment with 4 groups. All students worked on the homework sets. All students received immediate verification feedback on their answers. And then half of the students received the domain reasoner's inner loop feedback. And half of the students had student models available. And then, then we looked at their exam results in the course. We also used their exam results from the previous course. And we looked at student characteristics such as how long they worked in the online learning environment and which group they belonged to. Because we had 3 groups of students in this course: psychology students, students in educational sciences, and students in general social sciences. And the students in the psychology group were the participants of the experiment I showed first. So they already had experience with the domain reasoner feedback, and students in the other groups did not. So then we looked at these exam results and also at the number of hypothesis testing tasks they solved, and we found that these students, these psychology students who already had experience with the domain reasoner, so they already know the feedback of the domain reasoner, they benefited from its feedback, while the students who saw the domain reasoner feedback for the first time, they did not. So from that we concluded that students need time, maybe guidance. So psychology students also had a little more guidance in what the domain reasoner feedback told them. So students need time, guidance to benefit from that feedback. For the outer loop feedback, we have exam result here and the exam result from the previous course there. And for both students with and without student models, we found that prior performance was a good predictor of the exam results, as you would expect. So students who performed good at the previous exam also performed well at the current exam. But for the weaker students, the student models seem to be helpful. So for the weaker students, they seem to make better choices on, the student models seem to help them with either selecting appropriate tasks or reading material, or the student models may have stimulated them to just do more, just practice more, because they saw in the student models, oh, this is not good enough yet, so I need to do more. For the stronger students, well, it's a regression model, so yeah, it's all pretty tentative, these results. But for the stronger students, they seemed to be hindered a little bit by the student models, which could be explained. We think that the student models may have been a little bit too optimistic for these students. So these student models may have given these students the impression too soon that they were prepared well enough for their exams. Nog hier?
Does the student model come with a suggestion of what to do if you have deficiency on one subject?
Does the student model come with a suggestion on what to do if you have a deficiency in a subject? In this experiment it didn't. In one of our previous experiments there were lists available saying these extra tasks are for these topics, but these lists weren't as clear as I would have hoped in the beginning. So these could have been much more clear, and we think that that also could have helped students to better find appropriate practice material for their deficiencies. Now we were also interested in the two feedback types combined, because we had designed two new feedback types, we were wondering whether they would interfere, whether they could strengthen each other's effects. Now, for both feedback types, we didn't find effects, overall effects on the exam results. So students with and without student models on average performed equally well on the final exam, and students with and without domain reasoner as well. For the time that students worked in the DME, we found that or for the students' use of the feedback types, I have to say, we found that students who worked a lot in the learning environment, when they had the domain reasoner available, they tended to look at their student models less often than when they did not have the domain reasoner available. So that suggests that having both available, then they may fight for their attention, for the students' attention a little bit, compete for the students' attention, I have to say. So the students may not be able to process it all when everything is available to them and everything is new to them. But I will come back to what's said here. The results varied widely between students. So some students benefited from the one, some students benefited from the other. And for both feedback types, they did not have very much time to get used to it. So coming back to this question, do students benefit from the availability of the domain reasoner and the inspectable student models? We did see that the students used the feedback, that the students valued the feedback, that the effects varied widely, that the weaker students seemed to benefit from the student models, and that the prior experience helped for the domain reasoner. And now I can try to answer my second question again. How can computers be used to provide intelligent feedback about statistical proficiency? I do believe that providing both the domain reasoner feedback and the inspectable student models is useful, but I do also believe that students really need to be given time to find out what is useful for them individually. They need to be given guidance on how to use both feedback types. They should be given opportunities to use the information from the student models in selecting appropriate subsequent tasks. And finally, I think it would be very valuable to use the student data to improve the feedback. For example, by providing interfaces for doing learning curve analysis, like I just showed. So I wanted to end with what's next, because well, what's resulting from my PhD research, rather besides my thesis, which is in preparation to be printed and is being read by the reading committee right now. So we're hoping that all goes well. But the domain reasoner is ready to use, and also this steps interface is ready to use, and I really hope that people who are using NumWorks will start using this stepwise interface, and I really hope that I will hear about the experiences. I'm looking at you, Rogier, because I think that you showed some interest in it earlier, so I hope that you will do so. The outer loop feedback is also being implemented in NumWorks. Peter is working on a big project to use it in secondary education. And as I said before, I hope that in the future it will offer software to do the analysis, like the learning curve analysis. Well, and then finally, for me, what's next? If all goes well, I will defend my thesis on June 24th. And on the 1st of May, I will start a new job at the Hogeschool Utrecht, where I will be teaching in the Master Data-Driven Business and in the Bachelor Human Resource Management. Thank you. Any questions? And feel free to ask questions in Dutch, if you like. Nonneke.
Yeah, I was wondering, because there was no result measurable in the final exams for the feedback type, and even not compared to the control group, if I got it well. And I was thinking, was that maybe due to that at some points the feedback might be given too early? Because with the example you gave, I got the impression that maybe if you only give the feedback it's incorrect, then the student has to think why. And if you give a feedback, even with this question, you already know, oh, it should be one of those two.
So your question is, aren't you telling the student already too much by giving feedback immediately after the student made a mistake in the reasoning?
Yeah.
Yes. I think, so these tasks on hypothesis testing were not the first tasks they did on hypothesis testing. So, but before, the tasks were all very structured. So they should have some understanding of how hypothesis testing works by the time they start working with the hypothesis testing task. So I think this is an appropriate moment to pinpoint such errors that they still make, because it's not the first time they do so, to pinpoint them immediately to address, okay, something is going wrong here. Apparently you are not able to do this by yourself yet. The tasks are given at a moment that students should kind of start to be able to completely do it by themselves. So I think at that moment it is valuable to provide that feedback immediately. But it could be interesting to also design the possibility to let the student try to solve the whole hypothesis test. So to construct a complete hypothesis test, and then afterwards providing feedback on the one task, pinpointing where something went wrong. We didn't do so, but I think that could be a valuable next step to remove the immediacy of the feedback gradually, maybe. Does that answer your question? Rogier.
Yeah, just in response to this, I read a paper where they, instead of, you had an option in your feedback, there was also a reference guide. And then if you made a mistake like that, they give you a reference to the reference. So go and read that again, because that will teach you how to solve the specific issue. So instead of that's maybe a sort of a form of feedback that activates the student even more than given like these two options.
Yes, okay. So you could include references to the reading material, yes, to help the student better to decide what actions to take to resolve the misunderstandings that the student has.
Could be a form of feedback.
Could
Also
be
domain reasoning.
Yes, could be a useful addition. Yeah, so I think that many of the additions that we could make to both feedback systems concern not really what feedback is given, because I think we spend a lot of effort in the design to generate feedback that, or to analyze the evidence that we had to find out where the student went wrong or what the student doesn't understand well, but then on what actions can the student take after receiving this feedback. I think that a lot of design or a lot of improvement can be made there, which is another huge design challenge, but I think it could be worthwhile. Miriel.
Yeah, I have two questions related to this domain reasoner. So one is it a kind of stable thing that is the same for a learner, an expert, a mathematician, a social scientist? Is it reflecting the reasoning of all these different characters? And the other one is, to what extent is it, well, what is the predictable value of it? Because I know from a long time ago already a kind of similar thing for subtraction problems. And there it turned out that most mistakes were very specific for a task related to the specific numbers and their relations, and it was really difficult to get some general characteristics of tasks or problems and how to solve, what kind of mistakes children might make.
Okay. So your first question is whether the domain reasoner is the same for a mathematician or reflects the same reasoning of a mathematician, a student, an expert. The idea behind that is that the domain reasoner, and especially the rules in the domain reasoner, reflect expert reasoning. So rules, actually together with the strategy, but they define how would an expert in statistics, so a mathematician or a social scientist, solve this hypothesis testing task.
So you don't have something like make a picture first. I don't know how this would be in statistics, but in another mathematics topics I could expect that make a picture first is very important. Try an easy example, but that is specific for learners and not for experts, or maybe also.
Yeah, so you're talking maybe about heuristics that an expert would use. Currently our domain reasoner focuses pretty much on the procedure. What I find, well, a bit jammer for myself is that it really stops at the moment that you draw a conclusion about the null hypothesis. While it would be much more meaningful to think of, okay, now I have rejected my null hypothesis, what does this mean in the context of the task? But including that reflection also asks that we are better able to interpret the context of the task. So I would say that we have limited the domain reasoner right now really to the mathematics or the logical reasoning of the procedure. And that also excludes the draw a graph of the distribution under the null hypothesis. So it really is limited, I guess, to the logical reasoning of the procedure and then to the way an expert would reason, but it does allow for adding more steps in between or taking different routes, adding the steps in different orders. It does allow for that. It knows what is still acceptable and what is not. And in that sense, it accommodates and it knows how an expert would reason. So what I didn't tell now is that it can provide hints. When a student is working and stuck somewhere in the middle, the domain reasoner can provide a hint. This would be a logical next step right now. And that would be an expert step. But the domain reasoner is also capable of recognizing all small sideways steps that a student could take. So that's regarding your first question. And then your second question.
To what extent can it really predict the kind of error?
Can it really predict the kind of errors that students make? Yes, and you mentioned the example of subtraction, the domain of subtraction.
You showed this 1.33 and 2.33. I can imagine that happens, but there are many of these mistakes that students make because of superficial looking at the numbers and then trying to combine them in a certain way.
Yes.
So I expect that it's not always easy to predict that in advance.
No, that's not easy. And actually, this buggy rule of confusing the test statistic and the critical value I'm not really sure, but I can imagine that we added it after looking at student data. Because here student data is of course also very, very informative. If we analyze what errors students make and we look at it with our didactical view, we can see, oh, but here we see this confusion, and we can add them. And I think that in this domain of hypothesis testing, the number, well, that's a guess, that the number of different conceptual errors that students can make is smaller than in the domain of subtract. Yeah, I'm not really sure about that, but yeah, so we felt that we could.
Did you, for instance, have a few focus students that could be very taught? To what extent were the hints helpful, or were they?
Yes, we did before doing the experiment with the domain reasoner. We did some pilots with previous versions of the domain reasoner, and with these students, we also had interviews on what did you understand or not understand, and also we looked at their work and just sat right beside them to see which errors they made and where confusion arose. Yeah.
More questions?
If there are no more questions, is this also available for teachers, like secondary school teachers?
I look at Peter. Yes?
Well, especially het stappenvak, what Sietske showed, will be available in one of our subscriptions in the previous.
But I also meant the modules you made for statistics.
Okay.
Yeah, because I think that what you provide is not appropriate for secondary school students, but for teachers that would be quite helpful, I think.
Ah, yes.
Because there is a knowledge gap.
Yes. Well, the homework sets of the social sciences experiments are not freely available because they are property of the teachers in the social sciences groups, and they use a lot of tasks from their textbooks, so we cannot freely share these. We do, of course, have our own introductory statistics modules, and the domain reasoner software, as I said, is freely available. And I am very willing to share one or two of the hypothesis testing tasks that are also in the papers. So these are freely available.
And they can be made available in guest modules.
We will provide a link then, perhaps, with your...
Oh, sure.
We also put the video.
We did the same with the introductions. It's this introduction of the other project.
Yes.
You go ahead, I've also many questions already.
Okay, my question is something completely different. I know that many students don't like statistics because they think it's hard, they know it's hard, and some of the students you had already did some statistics and they have maybe a certain attitude to this topic. Did you also interview students about whether or not their motivation changed, or if they prefer this way of working?
We did not do any measurements of student motivation. I was really, I really focused on their understanding or their statistical proficiency. What we did do was, for the student models, we gave a questionnaire in which we asked them whether they valued the student models, whether they appreciated them, and they did. They really agreed with the statements that the student models were clear and that they reflected the topics that were discussed in the lectures well, and they also agreed to a bit lesser extent with the statement that the values in the student model did reflect their understanding well. Yeah, and the other thing, the graph I showed of the students' use of the student models tells us that they like the student models being available. And then in general, I mean, a lot of research has been done on statistics anxiety, especially with this group of social sciences students. And I would say that by providing all this feedback, we adhere to advice that is given in this literature. For example, that regular low stakes assessments can help students overcome such statistics anxiety, because this is typically low stakes formative assessment.
I was wondering about making the student models. I noticed that there was just one word, like presentation or stuff, but it was actually the category for the students. So is that formulated in terms of a learning goal or a set of learning goals? So does it mean more to the students than the category?
Yeah, that's way back, huh? Oh, it's not 2, it's halfway. So this is how it was presented to the students. But to get here, they had to press this button to get a scheme. And then on the last page of each homework set, we had a list with the same topics, and then for each topic an explanation of what we meant by the topic. So we had a larger overview. I don't know whether they looked at it. I didn't log that. But it was available for them. And also at that last page, so we said, okay, this is the overview of the topics in this module. Click the partial scores button to see your student model, and then use it to think of which topics you still want to read about or do tasks about. So we really encourage the students within the homework sets to use the student models.
So when this Sosnovsky said he'd never seen increasing
learning
curves, was that for was he always looking at single tasks or something? Or was it
no, he was, I think he was looking at tasks in which students, tasks that students only attempted once. So that's a bit different in our situation here, is that students could keep trying to answer these tasks until they were correct. And that in some cases the number of attempts could be pretty large if it was an open question. And I think that he looked at either at multiple choice questions. Yeah, I think it may have been multiple choice questions, but probably questions that students could try to answer once. And if it was correct, it's okay. And if it was incorrect, the system would tell them that it was incorrect and what the correct answer was. So they were not giving this opportunity to try until they found the correct answer themselves. And I think that makes a huge difference for the learning curve.
Right.
Yes?
Yeah, I'm sure I should know this, but if in the in calculating the percentages in the student model, you take into account the number of trials for a specific task that the student needed?
Yes. The calculation method, and now you have to pay close attention because we're going to do this by head, is, for example, for this 81%, all tasks connected to the knowledge component properties of variables are taken into account. For all these tasks, we look at all the attempts that the student made on that task. Incorrect attempts count as 0, correct attempts count as 1. And then we average all these attempt scores. So if a student answers incorrectly then correctly, the task score is 0.5. And if the student has 3 incorrect attempts, the task score is 0.25. And then we take the mean of all these task scores that are connected to the knowledge component. So 81% probably means that the student answered most tasks correctly immediately and made 1 or 2 mistakes somewhere in 1 or 2
But
tasks.
then it's a weird number, because if you do all correct, except for the last one, there are 20 tasks, and the last one you do 20 attempts, and only the 20 is correct, and you get the 50%.
No, because the task scores, all tasks weigh equally.
Okay.
So all task scores are averaged. Mean is taken.
But the back behind this question is the idea, how would, because of the interplay of the domain regional feedback and the student model, so how would the domain regional feedback impact on the number of trials and the final result of students, and as such on this percentage? So would there be a possible interaction between these two, which might cause, for example, the student model being less informative in the domain regional condition or something like that?
Well, in both conditions, there's the problem of the immediate feedback, which means that if a student answers correctly immediately, we know quite sure that the student knows. But if the second or third attempt is correct, it may be because, well, he looked, so the first attempt was incorrect, so he may have asked a peer to help. In the case of the domain regional feedback, this may be more direct because the feedback may give a useful hint on why it's correct. So that's, but I think it's a problem in both cases. That for second or third or fourth correct attempts, we have less information of whether that correct attempt is comes from correct reasoning or just from using the feedback well, so whether the student understands or not. So I think that is something to keep in mind when using student models in this setting. And actually that's why I'm always happy that we're using the student models to inform the students and to help them reflect on what they know and do not know. For example, a student might know that it's 17%, saying, oh yes, I struggle a lot with these tasks on finding the measure of center, but now I know. So the student may know more than what's in the student model. And that is a big problem if you are using the student model for selecting tasks that the student has to work on, so for giving tasks to students, which is often done. So in many computer-based learning environments, the student models are used to select tasks for students and then give these tasks to students. But in our case, because it's only used to inform, we think it's something to take into account and something maybe also to be open about to students, but less of a problem than it would be if we based task selection on this.
So could you more generally reflect on when you think this sort of diagnosis of what a student can do can be done automated, and when like what are the constraints for this sort of task that you can still do it?
Well, I'm pretty optimistic about that. If you can, because my basic philosophy behind that is that if you can give tasks in a computer-based learning environment and you ask students to provide answers in that computer-based learning environment, then the answers that the students give are evidence of what the student knows and does not know. And that goes for all tasks that you can imagine and all domains that you can imagine. If you can put the tasks in a computer-based learning environment, then you are collecting evidence of what the students know. But in any case, I would then suggest to, after you've done this, after you've worked with it with students, do a learning curve analysis to see whether indeed this assumption holds true for that domain as well.
I actually, thank you, but I actually meant the domain reasoner bit.
So then there should be some logical reasoning involved. That's a more difficult question. But still, I would say if you would have some stepwise procedure for which you can define steps that a student could choose from. And you can define what the underlying reasoning should be. I think you could come far, especially with the constraints system. If you can define what constraints the solutions should satisfy to be essentially correct, then you could design it. Does that answer your question?
So these constraints have to be complete.
Yes.
In a way.
Yes.
You have to be able to formulate complete
Yeah.
constraints.
Yes, that's an assumption we make.
Any more questions?
Well, yeah, I was thinking also about the answer. Well, I was wondering, the fact that you need to implement it in your system, does that also not limit, in a way, your thinking about possible tasks and ways of dealing with learning about statistics?
Now I'm thinking back of
I think of a lot of kind of problems that are not so easy to implement.
Yes, and we would quickly discard them then because it's difficult to implement. We did implement some tasks on, graphing distributions, for example, and we indeed found that these were difficult to connect to the student models. So I think you're right that is a risk, that you may narrow the view of what statistical thinking or statistical proficiency is. So yeah, again, I think that would be good to keep in mind and to, you could give additional tasks on paper or other ways. Yeah, so that's one thing to mention here is that this should always be integrated within a larger course with lectures as well. With I don't think that, the computer system is my teaching assistant, but it's not the course. No.
So we have drinks at 5, they're very strict, and that's so there should be drinks in 2 minutes.
May I suggest for next week, for next time, to order the drinks at quarter to 5?
Yeah, then they can't be.
Then they cannot be alcoholic. Maybe.
You can start a quarter later.
Yeah.
Yeah, but actually I enjoyed every minute of this talk, so
Thank
I
you.
would like to say thank you. Yeah, you too.
For 2 minutes applause.
Oh, you're welcome. Thank you.